to it, we can't inject code into it. So, enter the ZA router driver. TrueVector, in this version, does not mind if we load a driver. So yeah, it's kind of game over now. We can write to the system service dispatch table, so that means we can execute code on its level and unhook every single function that it hooked. So, and it's actually kind of funny. If you do this and are able to get this code to run, you can literally delete every single program file that ZoneAlarm has, and you're not going to be able to if you don't unhook all of them, but it's actually quite funny to see. So just a little pseudo rootkit driver code here. I'm calling it a pseudo rootkit because it doesn't do anything too malicious. It just unhooks a system call. So what we're going to do is create a memory descriptor list for this system service dispatch table, which is basically held in this DLL import right here that I believe is gotten from ntosKernel.exe. So what we can basically do is unhook ntopenprocess and replace it with the address of the original ntopenprocess. What TrueVector does is it basically redirects ntopenprocess into its own safe version. So the original address of this must be known ahead of time, and it differs between service packs. You're probably going. The method I use for this is to use hard-coded addresses. So if you run this on your box, you're probably going to blue screen yourself if you don't know what you're doing. You know, I was kind of too lazy to insert code in there that, you know, search the whole process memory space for, you know, some token that would identify the original ntopenprocess. But then we have this macro right here that basically you give it a syscall number and you give it an address, and it sets, you know, that syscall number to point to that address. So now that we have a way to inject code into ZoneAlarm, we have to find some code that's going to shut it down. Now, after doing a whole bunch of reverse engineering of this firewall, basically there is a location at memory 0x0040C261. That number will always be ingrained in my mind because I had to look at it so many times. But basically, the fun part here is you pass it a parameter of 4, and as you can see, there's this little string tvtf force shutdown. Sounds pretty interesting, doesn't it? That's pretty much what it does. In fact, if you inject this code and run it, you will find that ZoneAlarm is not killed. It stays running. But you'll see that there are still some problems that we're going to run into using this method. But if we can inject a call to this with a parameter of 4 being passed to it, we're going to own them. So the problem that number 2 that's going to appear here is that a whole bunch of alerts are going to pop up during this whole process of subverting the firewall. You're going to have a lot of icon changes. You're going to have this text box that magically appears over the various parts of the system that you'll see later, and hovering text boxes, all this fun stuff. We gotta get rid of it. That's the bottom line. We really don't want the user to know that their box actually got owned by us. So the most obvious thing, at least if you have the firewall minimized, is that there's a little icon change right here. Now, if you can see, it says that little red box with a yellow X in it, and it says TrueVector Security Services shut down. That's kind of a giveaway that we just own their box. So how does the system do this? How does it change this icon from its normal state to this you know, yellow X state? There's actually a call called notify icon that will do this. You basically give it a message that you want to send to the icon, and then give it a notify icon data structure, or a pointer to it, that will give it different information, such as what image to replace it with, stuff like that. So if you can see here, there are 2 parameters that are being passed to this. Now, in assembly, in x86 assembly, basically that means your stack pointer got decremented by 8. All right, because you have these push that you have the, when you're calling a function in assembly language, at least in the standard calling convention that's used pretty much throughout Windows, what will happen is you push these 2 parameters onto what's called the stack. Basically, it's a temporary variable space in memory, and then it's called. The function is called. So what we can do is, if we just allow these 2 parameters to be pushed onto the stack, tell the stack to go back up to where its previous state was, guess what? We just disabled that call. So we've taken care of the icon notification that the user will have. Now, the other problem that's very significant in this case is the various screen text that's going to show here. Now, if you can see that, little system error, please reboot, and please restart your computer to ensure security coverage, that's a little bit of a giveaway. This is, these resource strings are in the what's called the .rsrc section of the PE. And for all of you who do not know, PE means portable executable. It is the file, the executable format that is used on Windows. Like if you run Linux, you're going to probably be using an ELF binary. If you're, well, running quite a bit older of a version, you might be using A.out binaries. And, just for different operating systems and what have you, there are different file formats for their executables. But what this means basically is we can overwrite these strings with the originals. So we just have to know what the originals are, and then we can, neutralize those in memory so the user does not see that they got owned. And one important thing is it uses draw text to write these to the screen, which kind of leads to another problem. If you can see here, system error please reboot is on red. Now what's the problem with this? This message right here is usually in green. So that would be another alert that we have to kind of take care of. So, but of course we have to find a solution to this. Now the route that I took for changing the color of this text was a user mode hook on draw text. So what it's basically going to do here is, through all this stuff, background on how these user mode hooks work. We're basically redoing kind of what ZoneAlarm did with their, hooking NT open process and, pointing us to a different one. And what we're going to do is put this hook on draw text and make it point to our version that does some interesting things to the text if it meets certain criteria. Now, the first thing you have to know whenever you're hooking a function or a system call, whatever you're going after, you really need to preserve the program state. You want the program to pretty much think nothing happened. All your different flags registers should be the same. I've had many instances where I've blown ZoneAlarm up because I did not preserve all the flags registers. And of course, if you don't preserve the registers, period, then you're just gone. So basically, the way I did this was using the Intel x86 opcodes of push A, push FD, pop FD, and pop A. The push A pushes all the registers onto the stack, so then we can restore them later. Push FD pushes the flags register onto the stack so we can restore it. Now, pop basically does the inverse of this. Basically takes the flags register off the stack and puts it back into where it should be in its flags register. And pop A does the likewise with, doing this to the general purpose registers or anything else that you're going to be dealing with. So now what we have to do is find the parameter that contains the string so we can actually see what it's trying to write out onto the screen. So basically, after this whole push add and pop push FD sequence, it's located at ESP plus 2C because of all, it's using the stack to store all these registers, right? So we got to kind of jump over all of those, right, to the real meat of the whole thing. So what we can do is check, do a dword pointer EBX, basically look at the address that EBX has in it, see what's there at that address, and look for all, just all, because I believe it says all systems are active or something to that extent when it's running normally. So what we can basically do is see if it's there, then we can use this little function called setTextColor to set the text to green. So basically, all you have to do is pass it a handle to the to whatever text you want, and then pass it the color that you want it to be. And so that's very easy to find. I believe you can use something like what is it, WinSpy or whatever, to look through the different. It'll do different things with the Windows windowing system, that you can do all sorts of things like see what process owns this window, stuff like that. And basically, after we do this, we do the rest of the stack setup that's necessary for the function to execute, and we win. Now, there's this really big issue that we have right here. So far, we've been able to, write all this code that's going to do this quasi-malicious stuff to the person's system. But transportation is a very big problem in this, because, we have to load a driver somehow, which, pretty much we're going to kind of do this the standard way. So it's going to involve writing stuff to the disk and all this other crap, and basically you're going to have a whole bunch of bytes to deal with that would probably make this a gargantuanly large payload if you wrote it in pure assembly, and it would be very, very ugly and unruly. All stuff, you have bad characters everywhere. Probably, cause the program to terminate wherever you are injecting this payload into. So what the method that I decided to use to combat this problem is remote DLL injection. Have all of you used Metasploit before? A lot of people know? Yes? Okay. Well, it seems like a lot of you haven't, but what Metasploit is basically a framework for developing and using exploits. So basically, you have these, payload libraries, and you have different exploits that you can use, and different encoders, stuff like that, so that it can pretty much automate the whole process of exploit development. One of its payloads is that it can remotely load a DLL onto another system. Now, if any of you have ever seen someone using Metasploit and just getting like a remote C connection, or remote, basically remote desktop connection to the other person's system, that's all done through DLL injection. They have how it's layered is, modeled is basically a stage model. What the idea is you say you have a very limited amount of space to insert this code, right? And what you want it to do is you're able to write like a very small chunk of code that will read in a whole bunch of code. So you can effectively, have this stage, load this stage, and so on. So what we'll do is we'll basically, do whatever it needs to do to get a connection to the attacker, read this other stage in, and then execute that. So what it does is first, after it's been injected, it will load this code that will basically read in a DLL over the network and load it. And it does this by hooking various types of load library and some other stuff, basically so it does not have to load this DLL from the disk. You're not touching the disk in the entire time that you're doing this. And that's very helpful because this will, throw off all sorts of antiviruses and other HIP systems that could possibly get in the way of us being able to execute this code. Now, after we get the DLL injected, we're going to, sorry, let's backtrack a little bit. We're going to include the driver. Remember, we have to load this driver to get our stuff to work. We're going to include that as a resource in the DLL. You can basically embed files and stuff like that, and text, as in the case of Zoarm here. So what you can do is use the find resource, load resource, lock resource, and write file functions to write to the disk. And basically what this will do is it will load this resource and then write it out to a file so that we can